Bismillahirrahmanirrahim. Assalamu alaikum students. Welcome to our 21st lecture of MTH108 Business Math 1. Today we will continue with our chapter 9, which is about matrix algebra. Let us review what we have studied so far in our previous two lectures of this chapter. In our previous two lectures we have studied about the matrices, their definition with some examples. Why do we need the matrices in our daily life, and what are the basic facts of matrices? For example, the order of a matrix or the elements of the matrix, or how we donate our matrix, or what are the notations of the matrices. What are the different types of matrices? For example, a row matrix, column matrix, diagonal matrix, and some important other types. In our previous two lectures we have also studied about the transpose of a matrix, some matrix operations, which mainly include addition, scalar multiplication, and the matrix multiplication. Then we have also seen some properties of matrix operations, and what do we mean by the matrix equation, how this matrix equation helps us to represent a system of equations. First we have seen that how we can represent our algebraic expression in the form of a matrix, in the matrix form. And then we have seen that how we can represent our linear equation in the matrix form. And then, generalizing the concept, we have seen that we can represent any system of equations in the matrix form, and the system of equations may be linear or non-linear. Today we will study about a very important topic about matrices, which is determinants. We will see what do we mean by the determinants, what are the methods to find the determinants, and some properties of the determinants. And we will also study about the Cramer's rule, that how this Cramer rule uses the property of determinants to help us solving the system of equations. So we start with our definition of determinant. Determinants are only solved or only obtained when the matrices are square matrices, that is, when the number of rows is same as the number of columns. So we are given a square matrix A, then the determinant function associates with the matrix A exactly one real valued function called the determinant, and it is denoted by this vertical bar. The vertical bar matrix notation and the vertical bar closed. So DET, the abbreviation of determinant and the name of the matrix A. What do we mean by this definition, that the determinant function is associating the matrix only one real valued? That is, now we have used the word function, which means that we have some set of inputs. Set of inputs is our square matrices. Okay, and this determinant function is doing what? Doing nothing but associating this square matrix one real valued function, that is giving us, which is a real valued number. So we are given a set of square matrices and the output is only a real valued number, which is the determinant of the matrix, and the determinant is only one and unique associated to the given matrix. For example, if we are given a matrix A, let us consider the simplest one, or a matrix of order 2 by 2. Remember that while dealing with the determinants, the matrices should be square matrices. If the matrices have order m cross n, where m is different from n, or if the, let's say, matrix has order 2 by 3, that is where the number of rows is different from number of columns, then for these type of matrices we cannot find the determinants. Suppose we are given with the matrix A with entries 2, 4, 3 and 5. This is a square matrix of order 2 by 2. Then determinant of A will be the real valued number written as this, that is the vertical bar, name of the matrix, and the vertical bar closed. And by solving the determinant, we will remove these or we will replace these parentheses with these vertical bars. That is, the entries say on the same position 2, 4, 3, 5, and now we have replaced the parentheses or the square brackets with the vertical bars. So whenever the matrix entries are enclosed within the vertical bars, which means that we are calculating or determining the determinant of the given function. Now determinants are mainly used in solving the system of equations, and they have many other applications in finding the inverse of the matrix or system of equations. Now we come to some simple examples of, since we have said that the determinant can be calculated only for square matrices, so we start with the very basic one. For example, if our matrix A is a square matrix of order 1, that is, it has one row and one column. That is, if our matrix A is this matrix A 1 1 having only one entry, then the determinant of this matrix will be nothing but the entry of the matrix. That is, the determinant of a matrix of order 1 is same as the entry of the matrix. For example, if we have our matrix A as, let's say, -10, then the determinant of A will be, now we are trying to calculate the determinant of this matrix A of order 1. So instead of these square brackets, we will replace them with the vertical bars, that is the entry -10 written inside the vertical bars, and this is nothing but just the entry itself, which is -10. So to find the determinant of matrices of order 1 is very easy, and just by looking at the matrix we can clearly say that what is the determinant of this matrix. Now we come to the second step, that is when we are given the matrices of order 2. Suppose we are given a matrix of order, square matrices of order 2, that is a matrix having 2 rows and 2 columns. Then we are given a 2 by 2 matrix having the form, let's say A is equals to A11, A12, A21 and A22. Then the determinant of this 2 by 2 matrix will be, okay, first I write it and then I explain what do we mean by this determinant. A11, A22 minus A21, A12. If we recall the basic facts about matrices from our previous lecture, we have defined the diagonal matrices or the diagonal entries of the matrix. Now in this case, in this square matrix of order 2 by 2, the diagonal entries are, or our main diagonal is this, A11 and A22. That is when I is equals to j. So in calculating the determinant of a matrix of order 2 by 2, first we have taken the product of the main diagonal, that is A11 and A22. Then if we look closely at our matrix, this A12 and A21 is our other diagonal, not the main diagonal but the other diagonal. Okay. Then we have subtracted the other diagonal, that is A21 and A12, subtracted the product of the other diagonal from the main diagonal. And this is our main diagonal. So how can we calculate the determinant of a matrix of order 2 by 2? Simply taking the product of both the diagonals the main diagonal and the other diagonal, and subtracting the other diagonal from the main diagonal. That is, the determinant of a matrix of order 2 by 2 is the difference of other diagonal from the main diagonal. For example, if we have a matrix A given as 1, minus 2, 3 and 4, and we are interested in knowing the determinant of this matrix, then we will simply apply the formula. The formula says that first we have to take the product of the main diagonal. Main diagonal has two entries, A11, which is 1 here, A22, which is 4 here, minus the product of the other diagonal. The other diagonal has entry A21, which is 3, and the entry A12, which is minus 2. And simplifying this, we obtain that the determinant of the matrix is a real number 10. Okay, consider example 2. We are given a matrix B. Now we are only restricting ourselves with the matrices of order 2 by 2. Okay. Now, if we are given a matrix B of order 2 by 2 with entries 2, 4, 4 and 8, and we are asked to find the determinant of this matrix, then the determinant of this matrix will be this product, that is 2 into 8 main diagonal, minus this product, minus 4 into 4, which is 16 minus 16, which is 0. Okay. One more example. We have a matrix C with entries 1, 0, 0, 1, and we are asked to find the determinant of this matrix. By looking at this matrix C, we can recognize that this is the identity matrix I2, that is the matrix of order 2 by 2, and the determinant of this matrix will be calculated using the same formula, that is the product of main diagonal 1 into 1 minus the product of the other diagonal, minus 0 into 0, which is 1. So from this we conclude that the determinant of an identity matrix is always equals to 1, no matter what is the order of the matrix, 1 by 1, 2 by 2, 3 by 3, or whatever the order of the matrix is. An identity matrix has determinant equals to 1. One more example. If we consider our matrix D with entries 0, 0, 0 and 0, that is all the entries are 0, then this is nothing but the 0 matrix, and the determinant will be calculated by using the same formula, that is the product of the main diagonal 0 into 0 minus the product of the other diagonal, which is 0. So the determinant of a 0 matrix is always 0, no matter whatever the order of the matrix is, and the determinant of the identity matrix is always 1. That is, the determinant of identity matrix is always 1, and the determinant of 0 matrix is always 0, irrespective of the order of the matrix. Okay, now we have seen that how we can calculate the determinant of matrices of order 1, determinant of matrices of order 2. Now we come to one step higher, that is, now we are interested in calculating the determinant of matrices of order greater than 2, and we will start with the matrices of order 3 by 3 first. Now the method of finding the determinant of matrices of order 2 by 2 is used in determining the determinants of matrices of order greater than 2. That is this procedure which we have done here, that is the product of main diagonal minus the product of the other diagonal. This concept of finding the determinant of order 2 by 2 will be used in finding the determinants of matrices of order greater than 2. Okay, we consider a matrix of order 3, that is a matrix having 3 rows and 3 columns. We are given a square matrix A of order n greater than 2, and we want to find the determinant of this matrix. Now, with a given entry of A, we associate the square matrix of order n minus 1 obtained by neglecting the row and the column in which the entry lies. What does this mean? For example, we have our matrix A. Our matrix A is of order 3 by 3, that is the entries A11, A12, A13, A21, A22, A23, A31, A32, A33. Now this is our matrix of order 3 by 3, that is n is greater than 2. And we want to find the determinant of this matrix, that is we are interested in knowing the determinant of this matrix. The wording says that given with a given entry of A, let's say some given entry A21, we associate the square matrix of order n minus 1. That is, with this entry A21, we will associate the square matrix of order 2 by 2. How we will obtain this square matrix of one order less? By neglecting the row and the column in which the entry lies. That is, by neglecting the row and the column in which the entry lies. That is, for example, with entry A21, we delete the row and the column containing it. That is, we delete the second row and the first column, and we are left with a matrix of order 1 less than the given matrix. That is, we will obtain a matrix of order 3 minus 1, that is a matrix of order 2 by 2. And how we will obtain this matrix? By, just look at our given matrix again, by ignoring the row in which the entry occurs. That is, here the row is second row, so we will ignore this row, and ignoring the column in which the entry occurs. Here the column is the first column, so we will ignore the first column, and we are left with 4 entries A12, A13, A32 and A33, and these entries will give us a square matrix of order 2 by 2. That is, the entries are A12, A13, A32 and A33. The entries with respect to the matrix with respect to the entry A21. So, with entry of a matrix, we associate a sub-matrix of order 1 less than the given matrix. How? By neglecting the row and the column in which the entry occurs. Okay. Now, let's say we are interested in some other entry. For example, with respect to the entry A22, we obtain an n minus 1, that is a 2 by 2 matrix, as that this gives us, okay, this gives us what? We have to look at our matrix again. With respect to A22, that is this entry, means we have to neglect the row containing the entry, that is the second row, and the column containing the entry, and we are left with a submatrix of order 2 by 2 having entries A11, A13, A31 and A33. Okay, we are left with the entries A11, A13, A31 and A33. Okay, similarly, if we are interested in finding the submatrix with respect to the entry A23, then we will obtain a matrix of order 2 by 2. How? That is, this is our entry A23, and we will delete the row containing this entry, that is the second row again, and the column containing this entry, that is the third column. And this time we are left with our entries A11, A12, A31 and A32. So with respect to the entry A23, we are left with the entries A11, A12, A21 and A31 and A32. Now what we have done so far, we have selected or pick any entry. That is, what does our statement says, that with a given entry of A, we associate a square matrix of order n-1. We have taken 3 entries A21, A22 and A23, and with these 3 entries we have associated the respective square matrices of order 1 less, that is of order 2 by 2. How? By neglecting the row and the column which containing that entry. One thing more which we need to know before determining the matrix, before finding the determinants of a matrix of order 3 by 3. With each entry, we associate the number determined by the subscript of the entry. That is, we have our entry Aij with double subscripts I and j. Now with each entry, we associate a number determined by the subscripts of the entry. That is, with respect to the entry Aij, the number is associated by -1 to the power I plus j. That is -1 to the power sum of rows and columns. For example, if we take our entry A21, then the number associated with this entry will be -1 to the power 2 plus 1, which is -1. With respect to the entry A22, the number associated will be 1. And with respect to the entry A23, the number associated will be -1 to the power 2 plus 3, which is -1. So with respect to with each entry, we associate the number, and after simplifying, we have seen that the number will be either -1 or equals to 1. So with each entry, we have associated a submatrix and a number determined by this formula, and the number is either equals to -1 or equals to 1. That is, whenever the entry has sum of subscripts odd, the number will be -1. Whenever the sum of subscripts is even, the entry will be 1. Okay. Now what we have done so far, we were given with the matrix of order 3 by 3, and with some particular entries, the determinant of the submatrices of order n-1, we call them a particular name. They are called the minors. That is, these 3 submatrices which we have figured out with respect to the entry A21, with respect to the entry A22, and with respect to the entry A23. With respect to these three entries, we have figured out the submatrices of order 2 by 2 and the determinant of these submatrices. By determinant we mean that is these entries will be written in the vertical bars, and so on with the rest of the two. Now these determinants are called the minors, and the product of the minor, that is the product of the determinant with the number associated with each entry Aij is called the cofactor of the entry. For example, the minor of A22 is, or for example the minor of A21 is the determinant of the submatrix A12, A13 vertical bars, A32, A33, and the cofactor we call it with C21. The cofactor is the product of the minor, that is this thing, with the number associated with it. The number we have associated with A21 is -1, that is -1 times the determinant of the submatrix A12, A13, A32, A33. So we were given with a matrix of order 3 by 3, and what we have done so far, we have selected 3 entries. With respect to these 3 entries, we have associated a submatrix of order 2 by 2, and we have calculated the determinant. The determinant of the submatrix is called the minor, and with each entry we have associated the number with respect to the formula -1 to the power I plus j, and the number is either equals to -1 or equals to 1. And using these two things, we have defined the cofactor with respect to that particular entry, which is nothing but the product of the number associated with it and the determinant of the submatrix, that is the minor. Now using these things, we will calculate the determinant of a matrix of order 3 by 3. So first we look at the method of cofactors. The method which we use to determine the determinant of a matrix of order greater than 2 is called the method of cofactors. To find the determinant of any square matrix A of order n greater than 2, we select any row or column of the matrix. As in the previous slides, we have selected our second row. Okay. There's no condition on selecting the row or column. We are free to choose. We can select only one row or column. Okay. Then we multiply each element in the row or column, if you have selected the column, by its corresponding cofactor. That is, we multiply each element with the number and the determinant of the minor. Then we sum all these products, that is of the elements with its cofactors, and the sum of all these products is the determinant of a matrix of order greater than 2. Okay. Now let's look at example, and from the example it will be clear what do we mean by these 3 steps. That is, first we have to select a row or a column, then we multiply each element with its cofactor, and then we sum all the products. Okay. For example, we are given a matrix A is equals to 3, 1, 2, second row as -1, 2, 4, and third row as 3, -2, 1. And we are asked to find the determinant of this matrix. How we will proceed? First we have to select a row or a column. We start with the first row. We select the first row, that is this row, with entries 3, 1 and 2. Okay. Now we have to find the cofactors of each entry. Our first entry is A11, which is 3. Okay. Now the minor or the submatrix associated with this entry will be, we have to neglect the first row and the first column, that is the first row and the first column, and we are left with a matrix of order 2 by 2 with entries 2, 4, -2 and 1. Then we have to find the determinant of this submatrix. We call it as C11. The determinant of C11 is nothing but the determinant of a matrix of order 2 by 2, that is the product of the main diagonal, which is equals to, we don't need this vertical bar, 2 into 1 minus the product of the other diagonal, that is -2 into 4. While writing the determinants, we have to be extra careful in the minus sign. Here this minus sign is coming from the formula, and this minus sign is coming with the entry -2. So if we look at this -2, most of you may write here plus, which is wrong. Between the products of the diagonals, we always have a minus sign. Okay, and then simplifying, we obtain 2 plus 8, which is equals to 10. Since we have started with our first row, that is this we have selected our first row, then what is the number associated with this entry A11? The number associated is nothing but -1 to the power 1 plus 1, which is 1. Okay. So we have found the cofactor of this entry A11, that is cofactor of entry A11 is the product of the number associated with it with the minor, that is the cofactor is 10. Now our next entry will be the entry A12, that is our this entry. First I highlight, that is this entry, which is equals to 1. First we have to associate the submatrix with this entry, that is we have to neglect the row containing this entry, that is the first row, and the column containing this entry, that is the second column, and we are left with 4 entries -1, 4, 3 and 1. So the entry C12 is -1, 4, 3 and 1. And then we have to find the determinant of this submatrix, which is -1 into 1, that is the product of the main diagonal, minus the product of the other diagonal, which is 3 into 4, which is, after simplifying, we obtain as -13. What will be the number associated with this entry? The number associated will be -1 to the power 1 plus 2, and it will be -1. Okay, now we can write the cofactor of our entry A12. The cofactor of our entry A12 is -1, the number associated with the minor, that is the determinant of the submatrix, which is 13. Okay. Now we look at our last entry of this row, which is the entry A13, which is equals to 2. We have our entry A13, which is equals to 2. Okay, the matrix associated with this entry, the submatrix associated with this entry, is obtained by neglecting the first row and the third column. That is, the first row is neglected and the third column is neglected, and we are left with this submatrix with entries -1, 2 and 3, -2. Okay, and now the determinant of this submatrix is -1 into -2 -3 into 2. Simplifying, we obtained 2 minus 6, which is -4. And the number associated with this entry is -1 to the power 1 plus 3, which is 1. So the cofactor of this entry A13 will be equals to the number associated with the minor, which is -4. Now third step is, if we go back, we have selected a row or a column. We have multiplied each element in a row or a column by its corresponding cofactor. Now we have to multiply each element, each entry with its cofactor. That is, the entry A11 was 3. 3 will be multiplied by its cofactor 10. The entry A12 was 1. This will be multiplied by its cofactor 13. That is, the entry A11 was 3 multiplied by its cofactor 10. The entry A12 was 1 multiplied by its cofactor 13, and the entry A13 is 2 multiplied by its cofactor -4. And the last step says that sum all the products, that is, of the element with its cofactors, which means that you simply have to put the plus sign in between, and this is nothing but the determinant of our matrix A of order 3 by 3. We will simplify it. We will obtain 30 plus 13 minus 8, which is equals to 35. So this is the determinant, the real valued associated with our given matrix A of order 3 by 3. Let us revise what we have done so far. We were given with the matrix A. We have selected a row or a column. In our case, we have selected first row, that is with the entries A11, A12 and A13. Now we have 3 entries, A11, A12 and A13. With each entry, we have to find the cofactor of this entry. To find the cofactor, we need 2 things. First, the number associated with that entry, which is easy to find. Second, the submatrix associated with that entry, that is, the submatrix obtained by deleting the row and the column containing that entry. Then we have to find the determinant of that submatrix, okay, which is called the minor. And with the help of the number and the minor, we find the cofactor of that particular entry, that is, the product of the number with the minor. The same process will be applied for the second 2 entries, that is the entry A12 and the entry A13. Once we have found the cofactors of all the entries, next step is to take the product of the or to multiply the entries with their respective cofactors. Okay. Okay, entry 1 A11 multiplied by its cofactor, entry A12 multiplied by its cofactor, and entry A13 multiplied by its cofactor. Last step is to add all these products, that is product of A11 with its cofactor added with the product of A12 with its cofactor added with the product of A13 with its cofactor. Simplifying, we obtain a real valued number, which is basically the determinant of that particular matrix. And this process of finding the determinants is used for any matrix of order greater than 2. Now we have solved the matrix of order 3 by 3. With the same technique, we can also find the determinant of a matrix of order 4 by 4, 5 by 5, and so on. For example, we are given a matrix B with entries 3, 0, 1, 2, 6, -2, -5, 4. We may extend it. Okay, third row is -1, 0, 2, 4, and we have a fourth row as well, 3, 0, -2, and 1. So this is a matrix of order 4 by 4, of order 4, that is 4 rows and 4 columns, a square matrix of order 4. And we are interested in finding the determinant of this matrix B. It is not difficult to find the determinant of a matrix of this order. Here, if we look carefully at the entries of our matrix, we can simplify our work. How? By selecting the suitable or appropriate row or the column. Okay, that is, the selection of row or column sometimes makes our work less, and we can easily find the determinant of that particular matrix. Now, if we look at our matrix and particularly at our second column, then the second column has 3 zeros and only the entry A22 is non-zero. So by starting with our second column, our work will be less and we can easily find the determinant of our matrix. Why? Because entry A12 is 0, entry 32 is 0, entry 42 is 0. And what we have done in our second step, that is the step after finding the cofactors of the respective entry. After finding the cofactors, we have multiplied the entries with their respective cofactors. In our matrix, if we will multiply the entry A12 with its cofactor, since the entry is 0, the result will be 0. So there is no need to find the cofactor of an entry which is 0. Similarly, if we look at our entry A32, the entry itself is 0. So multiplying this entry with its cofactor will be 0. So there is no need to find the cofactor of this entry again. Our third entry is A42, which is also 0. Multiplied by its cofactor will give us 0, which means that we don't have to find the cofactor of this entry as well. So we are left with only one non-zero entry, which is A22. And then we have to find the cofactor of this entry A22. Okay, our entries A12, the entry at third row second column, and the entry at fourth row second column, they are all 0. Our non-zero entry is A22, which is -2. What we have to do? We have to find two things. The number associated with this entry, the number will be -1 to the power 2 plus 2, which is 1. The submatrix Okay, the submatrix, let's say C22, will be obtained by deleting the row and the column containing this entry. Here the order of the given matrix is 4 by 4, which means that the submatrix obtained by deleting the row and the column containing the entry will be the matrix of order 1 less, that is the matrix of order 3 by 3. And the entry is A22, means we have to delete the second row and the second column. Okay, and we are left with the entries 3, 1, 2, minus 1, 2, 4, 3, minus 2, 1. That is, we have to find the determinant of this matrix of order 3 by 3, which will be called as the minor. If we look at our first example, this matrix of order 3 by 3 is nothing but our first example which we have just solved, that is with entries 3, 1, 2, minus 1, 2, 4, 3, minus 2, 1. So we have already calculated the determinant of this matrix, which is 35. Okay, now the last step is to multiply the entries with their respective cofactors. That is, the entry A12 will be multiplied with its cofactor. Let's say this is the cofactor of C12 minus the entry A22 multiplied by its cofactor, which is 35. Okay, the entry A12 will have a minus sign because the number associated with the entry A12 will be negative. Okay, the entry A32 will have a minus sign again, minus 0 times the cofactor associated with it, plus the entry A42, which is 0, and the cofactor associated with it. And adding all these products, we obtain the first, third and the fourth product will be 0, and we are left with only the second product, which is minus 70. So the determinant of this matrix of order 4 by 4 is minus 70. Since in the beginning we have said that the determinant is a real valued number, so negative values, rational values, decimal values are all allowed. Even determinant can be equals to 0. They are all allowed. In this example, we have seen that by selecting the appropriate row or the column simplifies our work for determining the determinant of the respective matrix. Now let's have a look at one more example. We have our matrix D given as with the entries 2, 0, 0, 1. The second row has entries 0, 1, 0, 3. The third row has entries 0, 0, 1, 2, and we have a fourth row as well with entries 1, 2, 3, 0. Now this is a matrix of order 4 by 4, and to find the determinant of this matrix, we have to select the right row or the column. Here we have different possibilities which can simplify our work. The possibility can be the first row, because the first row has 2 zeros, or the second row, or the third row, that is first or second or third row. With respect to the column, we again have 3 possibilities, that is the first column having 2 entries 0, the second column or the third column, that is the first or second or third column. From these 6 possibilities we can select any one and we can start our work. For example, we start with our first row. Okay, the first row has entries. A11 is 2, entry A12 is 0, entry A13 is 0 again, and the entry A14 is 1. Okay, now we have the entries, and for these 2 non-zero entries A11 and A14, we have to find their respective cofactors. Okay, for the entry A11, the number associated with this entry will be 1, because -1 to the power 1 plus 1 will be 1. The submatrix associated with this entry, a matrix of order 3 by 3, that is, we have to neglect the first row and the first column, and we are left with a matrix of order 3 by 3, which is 1 0 3 0 1 2 2 3 0, and we have to find the determinant of this matrix. Okay, first we find the determinant of this matrix. We can start with any row or column, because every row or column has at least 1 0. We start with first row, that is with this row, which means that the first entry A11 or C11, C11 has the sign 1, multiplied by the submatrix, the determinant of the submatrix, which is 1 into 0 minus 3 into 2, that is this. Okay, minus 0 into the cofactor, which will give us 0, plus 3. This entry has position ith position 1 and jth position 3, so the number associated with this entry will be plus 1, and ignoring the first row and the third column, we are left with 0. We are left with this submatrix, that is 0 into 3 minus 2 into 1. 0 into 3 minus 2 into 1, which is 1 stays as it is, minus 6 minus 0 plus 3 into minus 2, and simplifying we obtained minus 6 which is minus 12. Now next step which we have to do is to find the cofactor of our second non-zero entry A14. Okay, our entry A14 and the number associated with it will be minus 1, because 4 plus 1 is 5, odd, minus 1 will be the number. The cofactor will be the submatrix of order 3 by 3, that is, we have to neglect the first row and the fourth column, and we are left with this matrix. Matrix with entries 0 1 0 0 0 1 1 2 3, and looking at this 3 by 3 matrix, if we select our second row or first column, our work will be very much easy to find the determinant of this matrix. So we start with our first column, that is 1. The number associated with this 1, this has third row and first column, so the number will be 1, and the submatrix will be 1 0 0 1, which is 1. Okay, now next step is to multiply these cofactors with their respective entries. That is A11 is 2 into the cofactor minus 12, and the entry A14, which is 1 with the cofactor minus 1, and adding them we obtain that the determinant is minus 25 of this matrix of order 4 by 4. So what we have done in this example, we had a matrix of order 4 by 4. We have selected first row. You can select any row or column which has more zeros in it, because this will simplify our work. We have selected first row. Then in this case we have to find the cofactors of only two entries, A11 and A14. Okay. For the entry A11 we obtained a submatrix of order 3 by 3, and we have to find the determinant of this matrix. Now by finding the determinant of this matrix is a matrix in its own. That is, we have to consider these entries as a new with a new index. That is, 1 is an entry with position 1 1, 0 is the entry with position 1 2, and so on. We have calculated the determinant of this matrix, the number associated with it, okay, and we have calculated the cofactor. For the second non-zero entry A14, we have done the same, taken out our matrix of order 3 by 3 and the determinant of this matrix, which was very easy because we have two zeros in our first column or two zeros in our second row, and this gives us the determinant of our matrix multiplied with the sign, which is minus 1. Then we have taken the product of the respective entries with their cofactors. That is the entry A11 with the cofactor minus 12 and the entry A14 with the cofactor minus 1. Adding all these products, we obtain the determinant of our matrix of order 4 by 4. Now we will look at some properties of the determinants. The properties of the determinants are: if all the entries in any row or column of a matrix are 0, then the determinant of the matrix is 0. For example, if we have a matrix A with entries 5 0 4 0, then this matrix has a column with all the entries, second column with all the entries 0. So this implies that the determinant of this matrix will be 0. That is, whenever we have a matrix with any row or column having all the entries 0, then the determinant will be equals to 0. The second property says that if any two rows or columns of a matrix are identical, then in that case the determinant is again 0. What do we mean by this? For example, if we have a matrix A as 2 2 4, the second row with entries 1 5 8, and the third row with entries 2 2 and 4, then the determinant of this matrix will be 0. Why? Because the property says that if any two rows or the columns are identical, here the first row is same as the third row, so the determinant of this matrix will be automatically 0, and we don't have to find the cofactors and taking the product with the respective entries and then adding them. Our third property says that if any two rows or columns are interchanged, then the sign of the determinant changes. What do we mean by this? For example, we have a matrix A with entries 2 4 1 0. Okay, first we calculate the determinant of this matrix A, which will be 2 into 0 minus 1 into 4 which is -4. The property says that if we interchange any two rows or columns, for example, we obtain the matrix B by interchanging the columns. That is, the second column is written as the first one and the first column is written as the second column. Then the determinant of this matrix will be 4 into 1 minus 0 into 2, which is 4. If we look at our matrices A and B, what we have done in matrix B, we have simply interchanged the columns of our matrix A. And how this will affect on the determinant? The number remains the same but differs by a minus sign. That is, by interchanging any two rows or columns of a matrix, the determinant changes its sign. The fourth property says that if any row or column of a matrix A is multiplied by a constant, by a scalar k, then the determinant will be the scalar times the determinant of the matrix. That is, for example, we have our matrix A as the same matrix 2, 4, 1, 0, and we know the determinant of this matrix as -4. Let's take our scalar k is equals to 2, and we multiply this scalar by our second row. That is, we obtained a matrix B, which is obtained by the first row as it is and the second row with this multiplied with the scalar, which is 2, 4, 2, 0. What we have done here, we have multiplied a row or a column of a matrix by a scalar. Okay, and now we find the determinant of this matrix B. The determinant of this matrix B is 2 into 0 minus 2 into 4, which is -8. Okay, and the second side of the equality is we have taken the determinant and we multiply it with the scalar. That is, k into determinant of A is 2 into -4, which is -8, which shows that either we multiply the scalar inside and then take the determinant, or we take the determinant first and then multiply with the scalar is the same. Okay, our fifth property says that if any multiple of one row or column is added to another row or column, then the value of the determinant is unchanged. What do we mean by this? For example, we have our matrix A with the same entries 2, 4, 1, 0, and we are saying that a multiple of a row or a column is added to another row or a column. For example, we multiply our R2, this is our row 1, this is our row 2, by our constant k is equals to 2. The matrix we obtained will be 2, 4, 2, 0. Okay, and multiple of one row or column is added to another row, and now we will add this row to our first row. That is, the matrix we obtained as, we are adding row 1 to row 2. We have multiplied row 2 by a constant, and now we are adding this row to our first row. We obtained 4, 4, 2 and 0. And the property says that the determinant of this matrix B and the original matrix A will be the same. The determinant of our matrix A we know is -4. The determinant of this matrix B will be 0 into 4 minus, this should be 1 here. What we have done here, we have multiplied our second row by a scalar 2 and then added to our first row. So the change will be in our first row only, and the second row on which we have multiplied and then added will remain as it is. So the determinant of our matrix B will be 0 into 4 minus 1 into 4, which is minus 4, which means that the determinant in both the cases is the same. The sixth property says that if any row or column is a multiple of another row or column, then the determinant is 0. For example, we have our matrix A as with entries 3, minus 2, 4, 6, 8, 1, third row minus 6, minus 9, 6 and minus 12. Now the property says that if any row or column is a multiple of another row or column, then in that case the determinant will be 0. If we look at our matrix, then our third row is a multiple of our first row, that is multiplying first row by minus 3, we obtain our third row, which means that third row is a multiple of first row, so the determinant in this case will be automatically 0. We can also look at this by using our previous properties. For example, if we multiply our row 1 by 3 and add it to the R3, the matrix B which we will obtain will be multiplying this first row by 3 and adding R3 to it. That is, first row will be 0, 0 and 0. The second row will stay as it is, and the third row will be minus 9, 6 and 12. So this gives us a matrix with one row having the entries, all the entries 0, and the determinant of this matrix is 0 by our property 1. And we have seen in our chapter 3, where we have used the Gaussian transformation or Gaussian elimination for solving the system of equations, that by doing these row operations we obtain an equivalent matrix. So the matrix B is actually equivalent to matrix A, and in matrix B we can clearly see that one row has all the entries 0, which means that the determinant of this matrix will be 0, or the determinant of the original matrix A will be 0. Okay. Now our seventh property says that we are given two matrices A and B. Then the property says that the determinant of the product is same as product of the determinants. That is, we are given two matrices A and B, then either we take the product of the matrices and then the determinant, or either we take the determinants first and then the product. They both are the same. For example, we have our matrix A as the same matrix 2, 4, 1, 0, and we take our matrix B as 1, 0, 4, 2. Then the determinant of our matrix A is minus 4. The determinant of our matrix B is 2. Simply cross multiplication and the minus. Okay, so we have, and the product of the determinants, that is the determinant of A into determinant of B, is minus 8. So we have calculated our right hand side. Now we will calculate our left hand side. For this we have to take the product of our matrices first, AB. Now the matrix A is a square matrix of order 2 by 2. The matrix B is a square matrix of order 2 by 2. So the resultant matrix will be a square matrix of order 2 by 2, and the multiplication is allowed. And we will obtain the first entry as 2 into 1 plus 4 into 4. The second entry with first row, second column, 2 into 0 plus 4 into 2. 1 into 1 plus 0 into 4, 1 into 0 plus 0 into 2, and simplifying we obtain 2 plus 8. This is 4 into 2, 0 plus 8. This is 1 plus 0, 0 plus 0, which is 8, 1 and 0. And now we have to find the determinant of this matrix. That is, the determinant will be into 0 minus 1 into 8, which is minus 8. So the property says that the determinant of the product is same as the product of the determinants. Our eighth property says that we have a matrix A and we have taken the determinant of it. This is same as taken the transpose of the matrix and then the determinant, which means that the determinant of the matrix and of its transpose are same. The determinant of the matrix and of its transpose are the same. For example, we have our matrix A, the same matrix, 2, 4, 1, 0, and we know the determinant of this matrix, which is minus 4. Now what is the transpose of this matrix? The transpose is obtained by replacing the rows with the columns. So the first row will be first column now, and the second row will be second column now. And now the determinant of the transpose will be 2 into 0 minus 4 into 1, which is minus 4. So the eighth property says that the determinant of the matrix and of its transpose are always equal. Now we have seen enough properties of the determinants and few examples in which we have seen that how we can calculate the determinant of a matrix of order greater than 2. Particularly, we have seen the example of matrix of order 3 by 3 and the matrix of order 4 by 4. Now we come to our next topic, which is the Cramer's rule. Cramer's rule basically is a rule which helps us in solving the system of equations by using the determinants. Okay, what does the rule say? The rule says that we are given a system of linear equations. The rule does not apply to non-linear equations. We have a system of linear equations. Then we have seen in our previous lecture that given a system of linear equations or non-linear, we can represent this system of equations in the matrix form. So we can formulate the matrix equation Ax is equals to B, where A is a square matrix of order n by n, which is the matrix of coefficients. Okay. Here A, in our previous lecture we have seen that the matrix of coefficients A can have any order, but here the matrix A should be a square matrix. Otherwise we cannot calculate the determinant. Now our matrix X is the same as the matrix of unknowns, that is the column vector with n rows and 1 column. And our matrix B is the same, which is the matrix of constants, which is again our column vector, that is a matrix of n rows and 1 column. Now Cramer's rule provides a method of solving the system of n linear equations in n unknowns by using the determinants. How? Okay, we see that let this triangle or delta known as the delta denote the determinant of our matrix A. Now to find the unknown xi or the unknowns of the matrix X, we replace the ith column of our matrix A by our matrix of constants B. We calculate the ratio of the determinants, that is, we say xi is equals to delta I over delta, where delta I is the determinant of A when the ith column is replaced by B. Okay, and delta is the determinant of our matrix A. So if we have a system of two equations and two unknowns, then the unknown x1 will be obtained by replacing the first column with our matrix of constants, calculating the determinant of it, dividing by the determinant of our original matrix A. Now, if our delta, the determinant of the given matrix, is 0, then we cannot apply the method. We cannot use our Cramer's rule. Why? Because division by 0 is not allowed. Okay. Now, the system may have either no solution. In this, if the delta is equals to 0, that is the determinant of our given matrix is 0, we conclude two things. Either the system have no solution, or the system have infinitely many solutions. But the other case, when delta is different from 0, that is when the determinant of the given matrix is non-zero, the system has a unique solution. Okay. How we use our Cramer's rule to find the system of equations? Let's have a look at our example. Okay. Consider the system of equations 3x1 plus 2x2 is equals to 80, 2x1 plus 4x2 is equals to 80. So we have a system of two equations and two unknowns x1 and x2. And we are asked to find the values of x1 and x2 using our Cramer's rule. We have a system of equations. We can easily transform this system into the matrix equation. How? By writing it in the form Ax is equals to B, where the matrix A in this case will be a square matrix of order 2 by 2. That is the number of equations into number of unknowns. So number of unknowns or the number of coefficients are 3, 2, 2 and 4. This is our matrix A multiplied with the column matrix X of unknowns x1 and x2 in this case is equals to our column matrix B, with B1 is equals to 80 and B2 is equals to 80. Okay, given a system of equations, the first thing is we have to transform the system into the matrix form. We have done it. Okay, now we have to use the Cramer's rule. The Cramer's rule says that we have two unknowns x1 and x2 and we have to find these values. First thing which we have to do is to find the delta, which is the determinant of our matrix A. The determinant in this case is nothing but the determinant of a matrix of order 2 by 2, that is 3 into 4 minus 2 into 2. Simplifying, we obtain that the determinant of our given matrix is 8. Now the determinant is non-zero, which means that the solution will be unique. That is, the values of x1 and x2 obtained from this Cramer's rule will be unique. They will be the only values of x1 and x2 satisfying our given system of equations. Next step is to find the value of our unknown x1. We have to calculate the determinant delta 1 divided by the determinant delta. Okay, what is delta 1? Delta 1 is the determinant obtained since we are interested in the first unknown x1. So delta 1 is obtained by replacing the first column with the column of constants. That is, the values 3 and 2 will be replaced by the values of the constants. So the first column will be nothing but the column of constants and the second column stays as it is. Simplifying, since we have vertical bars here, which means that we have to take the determinant. Simplifying, we obtained 80 into 4 minus 80 into 2, which is 320 minus 160, which is 160. Okay, now x1 is delta 1 over delta. Delta 1 is 160 and delta is 8, which is 20. So the value of x1 is 20. Now we will find our delta 2 and then the value of our unknown x2. Now the value of x2 will be equals to delta 2 over delta. First we have to calculate delta 2. Delta 2 is the determinant of the matrix obtained by replacing the second column with the column of the constants. That is, the first column stays as it is and the second column will be replaced by the matrix of constants, which is 80 and 80. Taking the determinant, we obtained 3 into 80 minus 2 into 80, which is 240 minus 160, which is 80. So we have calculated the determinant of our delta 2. And now x2 is nothing but the ratio of the two determinants delta 2 and delta, which is 80 divided by 8, which is 10. So by using the Cramer's rule, which basically use the determinants, we have quickly solved our system of equations without any. We have quickly solved our system of equations, and the value of the unknowns are, that is our matrix X with entries x1 and x2 is x1 is 20 and x2 is 10. And this solution is a unique solution. Why? Because the determinant is different from 0. Now let's have a look at one more example. We are given a system of equations with x1 plus 2x2 is equals to 5, x1 minus x3 is equals to minus 15, minus x1 plus 3x2 plus 2x3 is equals to 40. This example we have solved in our previous lecture by using the matrix equations. And we are asked to find the values of our matrix of unknowns or the variables x1, x2 and x3. The first step is to write the system of equation in our matrix form, which is Ax is equals to B, where A is a square matrix of order 3 by 3, that is we have 3 equations and 3 unknowns, and A is the matrix of coefficients, which is 1, the coefficient of x2 is 2 and the coefficient of x3 is 0. From the second equation, the coefficient of x1 is 1, of x2 is 0 and of x3 is minus 1. From the third equation, the coefficient of x1 is minus 1, of x2 is 3 and of x3 is 2. Multiplied with our column matrix X of unknowns x1, x2, x3 equal to our matrix of constants, which is 5, minus 15 and 40. Okay. Now we have to use our Cramer's rule to find the values of 3 unknowns x1, x2 and x3. First thing which we have to do is to find the delta, which is the determinant of our given matrix A, that is the matrix of coefficients. The delta can be easily found by using the first row, that is 1 into 1, A11 will have the sign 1 into 0 into 2 minus 3 into minus 1 minus 2. Now 2 is the entry and minus is the sign of the respective entry, because this entry is A12, the number associated with this entry is minus 1, so minus 2, and And the determinant of a matrix of order 2 by 2, that is the minor, which is, neglecting first row and second column, we obtain 1 into 2 minus 1 into minus 1 plus 0, because the cofactor of this entry will be whatever the number is multiplied by 0 will be 0. Okay, simplifying, we obtained 3, 1 into 3 minus 2 into 2 minus 1, which is 3 minus 2 into 1, which is 1. Now the determinant of the matrix is different from 0, so the solution, that is the values of x1, x2 and x3 will be unique. Next step, that is we are interested in finding the value of x1. x1 is defined as delta 1 over delta, where delta 1 is the matrix, is the determinant of the matrix obtained by replacing our first column with the matrix of constants. So first column replaced by matrix of constants will be 5, minus 15, 40, and the second two columns remain as it is. And the determinant, again we will find the determinant with respect to the first row, because with respect to the first row it is easy to find. We obtain 5 into 3 minus 2 into minus 30 plus 40, which is 15 minus 2 into 10, which is 15 minus 20 is minus 5. And x1 is simply the ratio of the determinants of delta 1 over delta, which is minus 5 over 1, which is minus 5. Next we have to find the values of unknowns x2 and x3 by first calculating the determinants delta 2 and delta 3. Okay, what is our x2 here? x2 is delta 2 over delta, and delta 2 is the determinant of the matrix obtained by replacing our second column with the matrix of constants, which is 1, 1, minus 1. Second column replaced with the matrix of constants with 5, minus 15, 40, and the third column as it is 0, minus 1, 2, and now taking the determinant. We will take the determinant with respect to the first row, which will be 1 into minus 30 plus 40 minus 5 into 2 minus 1, which is 10 minus 5 into 1, which is 10 minus 5, which is 5. So our x2 is delta 2 over delta, which is 5 over 1 and 5. Now we will calculate our x3. x3 will be the ratio of the determinants delta 3 with delta. Okay, and delta 3 is the determinant of the matrix obtained by replacing this third column with our matrix of constants. That is, our first column will be as it is 1, 1, minus 1. Our second column will be 2, 0, 3, and the third column will be now replaced by the matrix of constants, which is 5, minus 15 and 40. And now calculating the determinant. Okay, in this case we can calculate the determinant easily by using the second row, because the second row has one entry 0, but we can also calculate the determinant by using any row or column. So we go with the first row. We obtain 1 into 45 minus 2 into 40 minus 15 plus 5 into 3, which is equals to 45 minus 2 into 25 plus 15, and simplifying we obtained ten. So our x3 is our ratio of delta 3 to delta, which is 10 by 1, which is 10. So if we look at our values of x1, x2 and x3, our matrix X of unknowns, x1, x2 and x3 is, the x1 was -5, x2 is 5 and x3 is 10. We obtain the same values or same solution as we have obtained in our previous lecture. So by using this Cramer rule, this simplifies our work. The only thing this Cramer rule needs, that our matrix of coefficients should be a square matrix, so that we can calculate the determinant of our given matrix. And the determinant of the matrix should be non-zero, because if the determinant will be 0, we cannot proceed further. With this we end our today's lecture, and let us quickly revise what we have studied today. Today we have studied the determinants of matrices. To define the determinant, the matrix should be a square matrix. Okay. Then we have seen some examples to find the determinants of matrices of different orders. To find the determinants of matrices of order greater than 2, we have to use the method of cofactors. Then we have seen some properties of the determinants, that by using these properties sometimes simplifies our work in calculating the determinant of the given matrix. In the end, we have seen the Cramer's rule, which is used in solving the system of equations. That is, when we have n equations in n unknowns, and the Cramer's rule basically uses the determinant to find the values of our unknowns. If the determinant of the matrix of coefficients is 0, we cannot use the Cramer's rule, and in this case we say that either the system has no solution or the system has infinitely many solutions. But if the determinant of the matrix of coefficients is non-zero, the system has a unique solution. With this we end our today's lecture, and we have some practice exercises from the section 9.4. In our next lecture, we will continue with our matrices, and we will deal with the inverses of the matrices. With this, Allah Hafiz students.